Welcome. Good morning, good afternoon. Nice to see you joining us today, whatever time zone you're calling in from. Really appreciate it. So today we're going to talk about building your own AWS, your own proxy in AWS. But let's start by introducing ourselves. So Mr. Gallo, next slide.
Absolutely. Oops, wrong screen. There you go. Well, Good morning, folks. My name is Henry Gallo. I'm the Director of Delivery here in the United States for Contino. My background is purely infrastructure. And then at some point in my life, in my career, I fell in love with infrastructure as code. How could you not, right? You build in environments through code. You're seeing them go live. You're destroying them. You're updating. Super awesome. Can't give it up.
Yeah, and I'm Mike Owens. I'm a principal consultant here at Contino. I joined in January, and it's been a really great year, as I'm sure it's been for a lot of other folks. And prior to joining Contino, I've spent the last 5 to 10 years working with DevOps transformations and large enterprises. So I've worn a lot of different hats. I've worked with architecture, I've worked with SRE, I've worked with pipeline. And so in my spare time, I love coding as a hobby. I play with Raspberry Pis and Arduinos. And so, yeah, that's a little bit about myself. So a little bit about Contino. It's a great company. We're a couple hundred folks sprinkled across the globe. We have offices in the UK, America, and Australia. And what the company's done is brought together, just people who get digital transformation. And so a lot of our focus, our business model is actually to just pull great people together to work with great companies. And unlike a lot of other firms where the consultants show up, learn all the good stuff and leave, our mission is to transfer that knowledge and help people build their own careers, and so that those competencies stay within the firms so they can do the things they want to do. So yeah, we continue to grow. We have a great track record, working with lots of clients. But today, we kind of want to share with you some things that we think you'll enjoy. And really the goal, as you're migrating to the cloud, security is an important issue. And so, one of the questions that pops up is, how do you reduce your attack surface area? And the key to that is, limiting outbound traffic. Right? So the question is, how do you do that? It's been done before in different ways, and we thought it'd just be fun to use the AWS toolkit. So we're going to walk through our design and actually implementation and do a live demo. So yeah, specifically to that, I'll start off going through the theory, just talk a bit about proxies and NATs, and then we'll talk about our design of our system, and then the benefits behind that design, and then the actual implementation, lessons learned, and then show you some live stuff. So yeah, just to level set, what are proxies? Next slide. So basically, just think of a proxy as intercepting traffic, and then with that, you can decide what do you want to do with it. And in our case, we're looking to, see if it's a legitimate request, and if so, let the request proceed, and if not, to block it. So specifically, this is what we call a transparent proxy. Other people call it inline proxy or forced proxy. And so the characteristics of a transparent proxy, our definition, right, is that applications are unaware. There's no environment configuration. It's very key that you understand that you're introducing a single point of failure. And with that, the design of the architecture needs to be fault tolerant, needs to have resiliency. And yeah, and the other point is want to be able to maintain it over its entire life cycle as easily as possible. Slide. So key to that are NATs, right? And so
Sorry about that.
That's okay. No, next slide. Yeah. So again, just
maybe
to
I can take that one, Owens, if you don't mind.
Yeah, go ahead.
So absolutely. So Mr. Owens, thank you for providing that context. Yes, proxies for monitoring egress traffic. There is obviously no egress traffic with the demo that we're going to implement here. But just to give you a little bit more of context, so we have a proxy, but we also have a NAT gateway. And just to set the stage right, a NAT gateway, or a network address translation gateway, enable instances in a private subnet to access the internet. So how do I explain this? So in AWS, we have the term of VPC, right? Virtual private cloud. And we have subnets, right? So we have private subnets and we have public subnets. The private subnets are devices that cannot be accessed from the internet. However, though, these devices need to access the internet for things like installing packages, maybe pulling code from GitHub, or just browsing to what have you. You have to do to do your work, right? What happens is we have to place a NAT gateway in a public subnet so that this instances in the private subnet can access the internet through these NATs, right? So what we're doing in this exercise is we're not only just allowing them to access the internet, but we also are going to monitor the traffic, because we want to control what in the internet these devices can access. And that's the whole concept here. So it's not just the proxy, it's not just the NAT, it's both in one device. And I hope that makes sense. So anyway, so that's a NAT, and there are different approaches to doing this. You can have a single NAT to allow multiple instances and multiple private subnets to access the internet. However, that introduces a single point of failure and it's not recommended. What we're doing in this exercise, or what you see in the demo, is that we have a one-to-one, right? So if we have one private subnet, we have one public subnet, therefore we have one NAT gateway. Or if we had two private subnets, then we'll have two public subnets with two NAT gateways. Therefore, if there's a failure in an availability zone, let's just say maybe US East 1A, the devices on US East 1B will continue to access the internet. Furthermore, we have auto scaling groups here on these NAT instances, right? And just to not go too much into details, and Mr. Owens, I want to ask you to pull me up once in a while if I go too deep.
Yeah. Enjoy the passion.
Actually, I think I'm jumping ahead too much, but let me just finish that thought, right? So the beauty of having multiple availability zones and having resiliency is that, yes, you can have an outage in one availability zone for like 2-3 minutes, but with resiliency and self-healing, the devices can come back right up and continue to serve traffic. Okay, I'll just move into the next slide, and Mr. Owens, you run with this one.
Yeah, so in looking at our design, right, we kind of discussed what would be the key features of our system. And so again, at the end of the day, right, you want to be able to block malicious or inappropriate websites. What we decided to do is the way we would segment access would be based on which private subnet you sit on. So if you will, depending on which neighborhood you're calling in from, you'll have different access levels. And all of that will be dynamic, right? And it's configurable in a text file. And as Henry pointed out, the system needs to be fault tolerant. So we'll talk about use of high availability zones and auto scaling, self-healing. And again, it's infrastructure as code. So again, the design sits on, at the end of the day, a text file that defines everything. And so the benefits to that is, if you discover the design's faulty, you can redesign it by changing the file, or if you need to make changes or modify it. So it's not, the cost of ownership, right, goes down because it's easy to maintain. So those are our 4 key primary, value creation activities.
Absolutely, thank you, Mr. Owen. Let's Mr. Owen introduce this demo that we're doing here. He did mention that we're using AWS, and when I placed this on LinkedIn, when I advertised it, I said, we're doing infrastructure as code and we're taking Squid Proxies for a ride. Absolutely, because we were trying to have fun. Like Mr. Owen said, this has been done in the past. Yes, you know what proxies are. Most people use proxies, but did you build it like this? Did you set it as a force proxy, inline proxy, right? And did you use these services? So the services that we're utilizing here today are AWS Lambda, AWS Secrets, Elastic Network Interfaces, Auto Scaling, and CloudWatch. And I don't know if you can see this diagram fairly well here, but you hear me speaking about private subnets and public subnets. Just to reiterate there, right? So if you have a public subnets usually have not usually, they have an internet gateway, right? They have egress traffic and ingress traffic that is originated from the internet. You can filter it, yes, but the whole concept is that you have egress and ingress. And that's this green area on the left. On the right, we have a private subnet. Now, with private subnets, you cannot access services or devices sitting on the subnet from the internet. You could, however, have a VPN and you can connect directly to them, but that's outside of this context. What we're doing here is we have clients. This will be your wood developers or you what have you, right? So you can't access these guys directly. Again, you could only access them via VPN, or maybe you can come in through a public subnet, some sort of bastion host, and then hop into a private subnet. What we're trying to do here, though, is we're trying to allow some egress traffic into the internet. For instance, if you have Debian-based operating systems and you want to do maybe apt-get install, what have you, you would have to allow the .ubuntu.com domain. Furthermore, if you have Red Hat-based operating systems, then you would have to allow the Amazon AWS.com domain. And actually, that's part of the exercise here. So just to summarize, you have a client here, you would be a developer. There's a routing table that says, hey, my traffic needs to be routed in X or Y. What we're doing for this exercise is we're saying everything that goes out to 0.0.0.0/0, meaning the entire world, anything that is egressing in this route table, it says send it to this elastic network interface. And that is the magic of what we're doing today, this elastic network interface. I'll explain that in detail when we get there. But just to continue to go through this diagram, right? So it goes through elastic network interface, which is attached to a single Squid instance. It happens to be an auto-scaling group of 1, right? What that means is resiliency. AWS knows that there is an auto-scaling group of 1. If that server should fail, should crash, it would be detected, and CloudWatch will be monitoring for that event. When there is an instance provisioning, autoscaling says, okay, I'm supposed to have 1, and I have 0. I need to bring 1 up. What happens is we have a bootstrapping script, which is the user data of this EC2 instance. And guys, feel free to post a message here if I'm going too fast. I really want you to understand this concept because this is the magic sauce, right? So the instance crashes, CloudWatch says, hey, there is an event, there is an instance provisioning. Let me call Lambda, right? And what is Lambda? Lambda is a compute service that lets you run code without provisioning or managing servers. What does that mean? It's just a Python script that queries AWS APIs and does something for me. In this scenario, what the Lambda function is doing, or what it was written for, is going to go into AWS, search for an elastic network interface that has a specific tag, and it's going to attach it to this new instance that is coming up. So the flow is as follows, right? Server crashes, CloudWatch sees the failure, and it's looking for instance provisioning. Calls Lambda function to say, hey, go look on the elastic network interface pool and attach one of those network interfaces to a system that comes up, right? So what happens here is this network interface, it has an ID. That ID is at the routing table, so I never have to update the route table. The systems can drop 1,000 times, 20,000, it doesn't matter how many times they drop. They'll come right back up and they'll continue to route traffic within 2 minutes because there is bootstrapping mechanisms that would leave it at the same state that it was provisioned. I'll continue to move forward here. And this is what I was referring to in regards to resiliency, right? So before this demo, I tested a failure. And how do I test a failure? Well, I just terminate the instance. I have a client and I have a proxy. And I'm doing a curl, right? Just a curl command, a for loop, if you will, just curl at github.com. Obviously, I get an HTTP status of 301s because it's redirect. I'm going through a proxy. And I terminate the instance. And I stop querying. It just stops, right? I measured from the drop to the rebuilding of the instance, and as the client continues to get the 301s, it took about 2 minutes and 39 seconds. So today, I'm praying to the demo gods. You know, I'll terminate that instance. We'll time it. I have a timer online really nice timer that I found online, and we'll see how long it takes. I don't think it would take more than 3 minutes. And just to give you a little bit of how availability works, I did calculate the availability on a single failure in 1 year. I know that's insane, right? But I just wanted to demonstrate how that may work. Let's say you have a single failure in 1 year. The year has 525,600 minutes, right? It took the instance 2 minutes and 39 seconds to come up. So the availability is the uptime divided by the uptime plus the downtime. So what we have here is we have the yearly 525,600 minutes minus 2 minutes and 39 seconds. That's 525,597.35 minutes. You divide that by the yearly count of minutes and it gives you a 5.9 availability. Obviously, you know, this is like the best case scenario. One failure, we're not even adding here error budget or what have you, and you may have 3, 4 failures, but this is how it is calculated. And just to show you in a year, 2 minute, 2.5 minute, 3 minute failure, not too bad. Absolutely. And actually, before I move forward, this is with a single availability zone. We have 2 availability zones for this demo. And I just wanted to reiterate there one more time. We have now 2 private subnets, 2 different developer teams. We have developer team A, developer team B. Should this proxy/NAT fail, this team would not experience an outage. They'll continue to route traffic until this one comes up. You can get a little creative, right? Absolutely. And I may have that for a future step. I'm actually in the middle of writing that script, which you could override this table and attach this elastic network interface to it to continue to route traffic, and that will give you less than a second downtime. But it adds a lot more complexity, and we're not going to get into that right now. Awesome. Now let's talk about the bootstrapping mechanism and what is bootstrapping. Systems come up, they're ephemeral, right? We don't care about this servers, if you will, this EC2 instances in the cloud. We don't want to treat them as pets. We don't want to keep in. This is not, you know, the 90s or the anymore, where we said, oh my God, I have uptime of 1 year, uptime of 2 years. Really don't care, right? You go ahead and crash as many times as you want. You're completely ephemeral. You configure it through code. You'd always come up the same, right? We have no drift. If anybody does anything manual into the system, it will be overwritten on the next cycle, what have you. So for the bootstrapping mechanism, that's the user data in AWS. We're obviously installing the package. So I'm getting a vanilla AMI, Amazon Machine Image, and it has the Amazon Linux operating system, which is a Red Hat variant. We're installing the packages, whatever we need to work with, the Squid, obviously. We're mocking an SSL certificate, which we'll get into more detail, because with this configuration, you could do both HTTP and HTTPS queries, where HTTPS becomes a TCP tunnel. We'll get into details after we do a demo. Then we'll do a Squid configuration, where there's the squid.conf file that needs to be dropped into the etc directory. That's a static file. It's actually semi-static. It has some dynamics into it, which I'll get into while we do a demo and we do the building live. And then we have IP rule forwarding. The configuration for Squid listens on 3128 for HTTP and 3129 for HTTPS. However, developers will be making requests on port 80 and port 443, so I need to forward the rules accordingly. And the last but not least, the cron job. This is the configuration change monitor, and this is where it starts to get exciting, right? So imagine you have ephemeral systems. No human logs into the systems, and you need to change the configurations. How does the system know that the configuration changed without logging into it, or maybe without using something like Ansible? I want it to be fully automated. This is where the beauty starts. I'm leveraging AWS secrets to add both the sites that we're allowing the folks to access, and like Mr. Owens said, we have CIDR blocks specific to each development team. So for instance, if team A lives in 10.0.2.0/24, they can access certain websites because you're sourcing from that CIDR. And if team B has, I don't know, that 3.0/24, they have access to completely different set of websites. What happens is if I wanted to update the site or source, or if I wanted to add the sites that specific teams can access, I can either do it through the UI in AWS, which I'm not a fan of UIs, but I may just do it for the demo. I could just go ahead and add a different domain. Let's say, for instance, I want the .3.0/24 to access, I don't know, Contino.io or Google.com. All I have to do is just add that domain to the AWS secrets. The cron job listens every 5 minutes. It doesn't listen, actually it triggers every 5 minutes. It makes an API call to AWS. AWS secrets natively, they version the changes, right? So my server goes and says, this is the version of the secrets that I have. What versions of the secrets do you have? Is it the same? Great, I'll go back to sleep. Is it different? Okay, well, let me pull the differences and let me restart the service. And within 5 minutes, you have the next configuration, and you can roll it back as well. Now, for this demo, I changed the cron job to be more aggressive. I think I changed it to a minute, just so we can do it live. So I'll go ahead and I'll change the configuration through code. I'll change it through a UI, and then I'll run a query from the client just so you can see deny, 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 and then 301 redirect. Awesome. These were the configuration update. Actually, I went too fast. I went too fast. This is the flow chart of the configuration update. I'll run through this really quickly because I just explained it. So the cron job initiates. I have a restart flag of 0, meaning, is it 0? Don't restart the service. Is it 1? Restart the service. And the reason why I've done this is because the logic behind it, right? If it's a single team, let's say just a single sider, team A, it would be okay to pull changes and restart the service. However, if I have 3 teams or 20 teams, I don't want to restart the service 20 times because there are 20 changes. So what I'm doing is at the beginning of the script, I'm setting a flag, is set to 0, and I'll restart. If there is any particular team that has a change, just continue to query without restarting. At the end, it verifies the flag. Is it set to restart? Then it restarts 1 time. So if one of the 20 teams has a change, it'll restart 1 time. If 20 out of 20 has a change, it'll also still restart only 1 time because of the restart flag. This is very, basic logic, if you will. Now, let me explain the Lambda function because I did talk about that. And I shared a little issue that I had while building this and getting this ready for the demo, which was quite interesting. And I call it Witchery, and I have the code for that later. So what happens in the Lambda function? I'll go through this really fast because I explained this already. Instance gets provisioned. There's an event that is catched by CloudWatch. CloudWatch, it's a monitoring service in AWS. CloudWatch then says, okay, I was listening for this event and it happened. Let me call the Lambda function to trigger the script that searches for an ENI that has a what have you tag and attach it to the instance that is coming up. Fully ephemeral. We don't know the instance ID. We don't know the IP addresses, and we really don't care. We just know that there is an instance coming up. We know that there is a pool of elastic network interfaces that have specific tags that will be attached to a specific interface as they come up. And again, I can tear it down 1,000 times, bring it up 1,000 times, and this will always happen. So anyway, you attach the ENI to a newly provisioned EC2, and that completes the cycle. Beautiful, right? The problem was if I did a Terraform destroyed, and for those of you who are not familiar with the Terraform concept, Terraform is just infrastructure as code, and Terraform just happens to be what I'm using. A native service to AWS is CloudFormation, and there are many out there, right? And you could actually do this with Ansible, which I prefer to use Terraform either way. So what happened was, now just think about what happens. The system fails, CloudWatch listens and attach the instance. But what happens when you first build the environment? There is no failures. So therefore, CloudWatch is not going to catch that. Therefore, Lambda is not going to provision or not going to reattach the elastic network interface to the instances. So every time when I was preparing for this demo, I would build the environment and I would say, where's my network interface? It's not here. And it's because the failure was not there and I had to trigger a failure. So I would provision the environment, trigger a failure, and then the Lambda function would attach the network interface. The problem was this is fully ephemeral. I had no way to identify the ID of this of the instances that were being provisioned. So I had to provision the instances. I had to add dependencies to this provisioning, then go back to AWS and query AWS for specific tags and get that ID of that instance, and then just say, hey, attach this network interface to that instance. You know, Witchery, if you will. That's the only way I could do it for this demo. But that's why I put both here, so you have your Lambda function, how it compares to Terraform. Awesome. I would say, are there any questions here? But we're just rolling through this, and we'll take questions. Absolutely. Mr. Owens, I need a moment to breathe here. So
yeah, exactly. Right. So yeah, really good stuff. Again, this is just to share with you our approach and kind of the context behind that. So again, to kind of summarize and simplify, the actual design, really just think about it as 3 parts, right? There's your VPC, which is the key part. And key to that is, you know, making sure your users are in the private subnet. That's probably the most safe place you can put them in. Problem is, they need to talk to the outside world. How do you do it in such a way that they're initiating the traffic in a legitimate way and nobody from the outside can initiate traffic, right? And the key to that is the Squid server, right? And so not just setting that up, we're looking at using auto scaling groups and CloudWatch, the Elastic Network Interface, IAM, Lambda, and routing, right? So we're going to actually walk through how all these things are configured through code, and ultimately test and validate. And the way we test and validate is we'll have 2 separate private subnets, each having different access privileges. And so we'll test for a positive and test for a negative. Just wrapping that up. Next slide. So the benefits, right? This is how we link our business problem with our technical problem. Again, coming back to the original problem, which is, you know, how do we ensure security? Again, the key here is that we want to allow access to specific domains. We want to be able to, when those don't occur, have a customizable error message. We want the user experience to be the same. So people who are making legitimate requests, they just see nothing. And also when things are not quite right, provide it in such a way that is useful and helpful, right, and guides them in the right, you know, build the right behaviors. But on the back end, you're able to monitor the behavior. You have a means to, you know, collect data, which can be beneficial for a lot of different reasons. And also, more importantly, is looking at the total life cycle of the system, right? And so really thinking through how do we add, delete, modify changes, right? And so in this design, the idea is that changes can be as simple as updating, you know, a file. We then trigger that update, and within, you know, 5 minutes, those changes then are realized in, you know, the live environment. And again, key is resiliency, right? So the system has some self-healing and fault tolerance. So at the end of the day, right, when we look at building systems, any system, you know, you want to look at 4 things. You know, is it fast? Is it secure? Is it reliable? And is it available? So again, I think our design links back into that. And so, yeah, again, at the end of the day, what does the business need? People just want to be able to do their job and have legitimate access and do it in a way that's not disruptive.
Absolutely, Mr. Owens. Thank you for that. Did you want me to take this one?
Yes, please. Yeah,
okay,
go ahead.
Absolutely. So yeah, so I get super excited, folks, and Owens, please feel free to pull me back. So some of the tech that I utilize for this project, or that we utilize for this project, obviously Terraform. It just happens to be my favorite. AWS, we use a little bit of Bash scripting, and absolutely Python, which is where I spend most of my time. It's specifically Boto 3, right? This is just how you communicate back to AWS, or how you make API calls to AWS, such as searching for an Elastic Network Interface, or maybe identifying a subnet ID, or identifying the ID of that EC2 instance as it is provisioned, or after it is provisioned. Absolutely. So let us go through this real quickly. I think Mr. Owens spoke about applying this in you know, I don't know, places that are supposed to be fairly secure, what have you, right? Highly regulated environments, if you will. With that in mind, I applied segregation of duties for this demo. And so I extrapolated the secrets, and just to refresh everyone's mind, I'm utilizing AWS secrets to manage the sites that are allowed to be visited by a specific team. And what I mean by a specific team is a source cider, right? What source subnet are you coming from? If you're coming from, the example shows here, you're coming from 10.0.2.0/24, then you're part of team A. That means that you can access github.com, you can access google.com, and again, actually this is wrong here because the application should have a 2.0.24. That means that this would never work if I'm sourcing from 2.0/24, but it's only allowing that 3.0/24. You will get permission denied, even if you have the domain and the allowed sites, because you're not coming in from the right cider. They're bound to each other. Team A sites have to match the source of team A. Otherwise, it wouldn't work. And I could demo that in a second. Anyway, I got a little derailed here, but I'm utilizing secrets for allowed sites and allowed ciders. And with that in mind, I created IAM policy that is very specific to the secrets that you can access. So basically what I'm saying is I have a Squid server that makes an API call to AWS secrets, and you should only access the secrets that are specific to the Squid proxy. Let me say that one more time. If I'm the Squid server, I can make an API to AWS secrets. There are many ways of doing this, and I could have said, hey, allowed access to all secrets in AWS, but that wouldn't be very secure, would it be? So when I create this policy, the policy is created in a dynamic manner. What happens is I create the secrets through code. The codes have specific ARNs, which we're utilizing outputs. And I don't want to get into the mechanics of inputs and outputs for Terraform, or maybe I should at a high level. Inputs are just variables that you add to the code, and outputs are information that is provided back to you after the infrastructure has been provisioned. The piece of infrastructure that we're extrapolating out of it is the ARN. So what we're saying in this policy is, hey, you can get the secret, so you can edit it, you can write to it, you can change it, you can only get it. You can get the value of the secrets for the specific resources, and those specific resources are these ARNs, right? And there are, it has ARN, AWS, what have you, with the account number. But what I wanted to highlight here is application 8 list, application 8 cider, application B list, and application B cider. Okay, if I was to add more secrets to my Terraform code, this policy would also change because again, it's dynamic. It would always read, how many secrets do you have? Give me the ARNs of those secrets. I'm going to add those ARNs to that policy so that the Squid server can access the secrets. Furthermore, this policy gets attached to a role. And a role are permissions that you attach to a server, an EC2 instance. The beauty of this is that we have this auto scaling, right? For this exercise, I have, how do I explain this very simply? If I have 3 private subnets, if I have 3 different, if I have 3, I'm saying 3 and I'm pointing 6. If I have 3 developer teams that live in 3 different ciders, that means 3 different subnets. It's going to create 3 network interfaces for me. It's going to create 3 EC2 instances distributed across the different availability zones. It will be US East 1A, B, and C. And it would have the same number of public subnets. So it will be a 1-to-1 match, right? The beauty of all of this is that, yes, I have a user data, which is your bootstrapping script, but I also have a set of permissions. So what that means is when I provision the instance, this permissions gets attached to the server. Again, it doesn't matter how many times the server crashes. It's going to go and read my launch configuration file. It's going to say, I'm supposed to have these permissions. So all 3 servers are equivalent. right? They're replicas of each other, and they have the same set of permissions. Isn't this amazing? It's just outstanding. And that's why I love infrastructure as code. By the way, folks, there is no manual intervention of anything that we're building today. Everything is fully automated. And like Mr. Owens said, it is self-healing. It'll be destroyed, it'll come back. It's gonna say, hey, these are my permissions, these are my configurations, this is what I can access. Do I need to restart my service? Amazing, outstanding. Okay, lessons learned. So while developing this, and yeah, I think this is the third time I'm going to say this, proxies have been around for a very long time. Everybody has done it, absolutely. But has it been resilient? Has it been highly available? Has anybody shared the code with you, right? Has anybody shown you the code or doing a demonstration like I'm about to do? Maybe, right? But while doing this and preparing this demo for you guys, I ran into a couple of problems. I always say, you know, when programming something, the language is very easy, very straightforward, any programming language. What's difficult is the logic. And that's what I was running into. I was having some logic problems. I didn't know how to handle a failure and then just keep the system up and running or have it self-heal. And I tried multiple things, right? So I did mention that the Squid server are replicas of each other. So I said to myself, hey, why don't I put these guys behind a network load balancer and have the clients access the Squid service through a network load balancer? Absolutely, I could absolutely do that. And it worked. The problem is that I couldn't add the network load balancer to a routing table. So therefore, I would have to set the environment variables of HTTP underscore proxy, HTTPS underscore proxy, which violates the whole thing that we're trying to do here, which is a transparent proxy or a forced proxy, inline proxy. The purpose of this proxy is that it is completely invisible to the user. You don't have to set the environment variables, not at the server level, not at the application level. All traffic is forced through a route table, and that route table is forwarding everything through a Squid. Everything is going to go through there, or you're just not going outside. Absolutely important. So network load balancer cannot be added to the routing tables. I also try to do AWS endpoints. Unfortunately, the only endpoints that were routable were S3 and Dynamo database, and I needed to route to a Squid server, EC2, ENI, maybe an Elastic IP, but that was not an option. So I did put some work into this. It was a great learning experience, but unfortunately, it just didn't support what I needed to do, which is the transparent proxy. Now, guys, it is important that you understand the difference between a proxy and a transparent proxy. If I had a regular proxy, I could have applied the network load balancer, no problem. Then again, you'd have to set up, or maybe even unset the proxy parameters. And you know, I just wanted to be forced and transparent. You know, don't worry about it. Awesome. And this is the Witchery which I'm talking about, right? I did call it Witchery.
Halloween
right?
stuff.
That's right. Well, it's almost Halloween. That's right. Now, what happens, right? So you're building a system. The system is fully ephemeral. You have no information about it. Now, there's a difference with AWS instance provisioning and auto-scaling provision. With AWS instance provision, you can get, if you remember when I spoke about outputs in Terraform, you can get that information back. When you're talking about auto-scaling groups, you're literally saying these are no pets whatsoever. I don't care. This is cattle, right? Don't give me any information about it because I don't want to know. Fully ephemeral, you crash, you burn, another one comes right back up. I have endless resources just to keep coming up. With that in mind, I needed to know exactly the instance ID. So there's a data query for AWS instances. And as you can see here, I did speak about dependencies. So if I query the instances before they exist, it would tell me, hey, there's no results for this query, and there's a non-zero exit code status failure, right? You're just gonna stop working. So what I needed to do is I said, hey, wait until the auto-scaling group is ready. I called it Squid, and then go back and query these tags. I just happened to name it Squid just because I was super creative, right? So I just call it Squid. And then after I got this query, I went back and I said, hey, how many network interfaces do you have out there? Okay. Now remember, I'm attaching a second network interface. By default, servers come up or EC2 instances and they have one. So that's ETH 0. I need to start at ETH 1. So you need to be specific about that, right? So I went ahead and I said, hey, go back to this data up here, this data AWS instances, and just give me the instance ID and attach that network interface to it. But again, this is fully ephemeral. Maybe there's a better way to do this, but I don't know. This was the best way that I could identify it with the time that I had. And again, this was just like the salt and pepper, if you will. I could have easily just built the infrastructure, cause a failure, and just have it provision the elastic network interface, but that would defeat the purpose of me saying here, there's zero human intervention. I wanted zero human intervention. So you build it, you destroy it, you have a failure, no humans involved. Maybe the human is the one destroying it, right? Absolutely. Some of the cool stuff that I went through, and I know this site is super, super busy, okay? But I just, let me just highlight each of them and then I'll explain in detail. So one of the first things that I did is variables of type maps, right? So when you're generating a private subnet, I thought this was really cool. In the past, I have said, hey, USDS1A is equals to a full CIDR block. And a CIDR block could, in this instance, is 10.0.0.3.0/24, right? What I'm saying here is I manipulated the third octet of this variable. So instead of writing out the whole CIDR block, I just said, hey, the third octet is 3 and the fourth octet is 4, which I thought it was really cool and I wanted to share that with you. Another feature that I thought was really cool, and this was with Terraform version 12, is the fact that you can enable and disable infrastructure. It's just a variable, right? So I have 3 modules. I have the VPC module, which generates all my networking layer. I have my Squid server, which has a whole bunch of Terraform resources. I'll go into detail in a little bit. And then we have the test clients. These are the clients, the developers who need to access the internet or what have you. After Terraform version 12, you could enable or disable infrastructure without actually doing a destroy. And I apologize for the folks who are not familiar with Terraform. Maybe we should do another one on Terraform. But anyway, it is easier now because you could just say true or false is a Boolean. So if I say, for instance, for the test client, I want it to be false and I still do a Terraform apply as opposed to a Terraform destroy, it'll identify that I don't want to have it. So it'll just destroy it for me. And I'll demo that in a second. Anyway, it looks like I'm running a little out of time, so I'm going to hurry it up a little bit. I'm going to skip some of this, but this one is important, right? This is the secrets ARN. And this is really cool because I was speaking about segregation of duties. So what I'm doing is I'm building the secrets through a different Terraform state file. Basically, my CISO's team would build that. My security team would say, I'm going to build the secrets for you. You're going to consume them. So I'm going to create outputs. I'm going to give you the ARNs only. What I can do in my Terraform code, I can import those outputs from a different state. Somebody else ran it. Somebody else has the information, but they gave me the ability to be able to go there and query the specific ARN so I can add it to the Squid server so that they would have access to those secrets, right? Via IAM policy and IAM role. Okay, I'm gonna fly through this now because we have 15 minutes left. Oh, this is cool. So we're already at demo time. All right. So awesome. All right, let me see how I'm gonna do this. I'm gonna minimize the screen. I'm not trying to make you dizzy, but let me just move some stuff out of the way. Sorry, maybe I shouldn't do that. You set up here. Awesome. All right, so the first demo, actually, let me just go back, was just to show the Squid configuration fairly quickly. Okay. So let me just show you what that looks like in AWS. And I'm going to refresh just to make sure that my session has not expired. And it seems that it has. Just bear with me a second. Nobody look at my password, please. Okay, great. So I'm at the AC2 console, right? And I have 4 instances running. What that means is that I'm working with 2 availability zones, right? So I have US East 1A and I have US East 1B. Notice that they're 1-to-1. So we have the Squid proxy and we have a test instance. And if we look at one of the test instances, the cited block is 10.0.4.0/24, and this instance has been allocated the last octet as 11, right? For the other test instance, I have that 3.0/24. That's a different subnet, right? Different cited as well. And notice also notice that there is no public IP address for this client. So again, if I wanted to access these clients directly, I would have to have some sort of VPN, or not some sort of, I would have to have a VPN. Or I could just, what I'm doing is in this exercise, the proxies live in a public subnet. They do have a public IP address. I could log in there and then I can hop into my private instance, okay? But without further ado, let me just copy the server on US A, right? And I believe it's this one, but I just want to verify. So I'm just going to SSH into that server, and I am in, right? I'm just going to show you the configuration, which exists in etc Squid. So obviously, for most Unix operating systems, configurations natively should be in the etc directory. Anyhow, I do have a couple of things here. So I have Squid allow sites application a.old. That means that the fetcher script went and got some configuration. It was different, so I just kind of made a copy. This is not best practice by any means. It's just playing around. You should ideally copy those somewhere else, or AWS secrets keeps version, so you should keep that version and just revert back to the version. It's supposed to make it a local copy, which it would be lost once you destroy the system. Anyway, so beauty of Squid, very straightforward. Can you guys see that well, Mr. Owens? Can you see that well?
Yeah, I think you're using the real estate best you can. I can see it.
Okay, great. So there's a configuration here for Team B, right? So Team B has sites that it can access. So those are sites from B, but it also is married to the source applications B, and then it applies this. Both of these ACLs come together and they're applied to the HTTP access, right? And that's just HTTP. So you have a list of sites, you have a list of source CIDRs, and then you can say, hey, this allowed application B sites can have HTTP access derived from this site. I don't know if that's a little confusing, but just to summarize, you have sites and you have CIDR source. So if you're sourcing from this IP address and also your list allows you to go to this site, then you'll be able to visit the website. Otherwise, you're going to be blocked. You're going to get an error, right? You're going to get some sort of 400. Another thing that I thought was really cool was the SSL, right? So that actually gave me a lot of problems. At some point, I was doing a curl to HTTPS, and it wouldn't understand it. It would say, "Hey, I have a certificate, right? Because I'm sourcing. I'm a client. I'm making an HTTPS request, but then you changing my certificate when I go into the proxy. This is not valid, right? So what we're doing here is a series of steps. It's a step 1, 2, and 3. And what happens is, I love the terms, right? So Squid uses the term peek, like I'm peeking, I'm looking at the certificate, right? So I'm gonna peek at step 1, and then I'm gonna bump it to a step 2. I'm gonna say, hey, I'm gonna allow this HTTPS site, but you know what? I'm gonna splice it. And what it means by splicing it is I want it to be fully transparent. So treat traffic as if there is no proxy in between, just create a TCP tunnel and allow that SSL connection to be to initiate, right? It removes the SNI, right? So that's super cool, super awesome. The configurations look as follows. So if I look at the source A, it just says, hey, I can access github.com, apple.com, contino.io, and google.com, right? If I look at the sources for application A as well, that will look like this. Okay, so in a nutshell, that's what it is. And I do have the client here. Okay, so this is a 10.0.3.10. It does match that 3.0/24. Now let's do a query. I'm going to look at the logs here. I'm going to look at the access log, right? There is nothing happening. I'm going to go into the client and I'm going to say, hey, give me, I don't know, go to google.com, right? And it's going to tell me that it's a 301. That means it redirected my traffic. I get a 301. That is awesome. Now, Mr. Owens, give me, I don't know, some URL to visit.
CNN.com.
CNN.com, right? I go to CNN.com, I said I get error denied because it's just not there, right? It won't allow me to access that website, and it tells you on the logs, this is a 403, you're denied. You cannot go to that website. So you have the right cider, you're coming from the right source, you're just not allowed to go to that website, okay? So now, let us get a little more creative, right? Let's say, for instance, I'm gonna go back up here, right? And I'm going to look at the allowed sites. This is something that you could apply live. So now I need to install packages. I know this is a Red Hat derivative operating system. That means I need to use Yum to install a package. Now I'm going to become sudo here, and I'm going to have to rush this because we only have 9 minutes left. Oh my God. Yum install nmap, right? I need to be rude. Yum install nmap, right? It tells me, and I'm not looking at the logs, it tells me that it's denied, right? I cannot install nmap, even though it's just the installation of an operating system is denying me. Okay, just because of the sake of time, I'm just gonna go into the UI and I'm gonna add Amazon AWS.com domain so I could add that package, okay? So I'm gonna go into services, oops, cancel that. Services, secrets manager. I'm going to go into application 8 lists. I'm going to retrieve the secret value. I'm going to edit it, and I'm going to add Amazon AWS.com, right? I'm going to save that. Now it's going to take 1 minute for the cron job to trigger. As you can see here, if I do a cron tab L, it's fetching every 1 minute. But again, I don't have time, so I'm just going to run it manually now. And Owens, can you check to see if there are any questions on the chat, please?
Sure.
Okay, great. So if I cut the contents of the application sites A, Squid allowed sites A, you can see that Amazon.com is there already, right? So if I do a sudo yum install nmap, now it's able to read the repository and install the packages for me. That's just one of the scenarios, okay? And I'm gonna rush through the next one. The next scenario, I'm gonna query it from here, maybe, how do I do this? I'm gonna start querying, a website on a for loop. And I'm gonna destroy the instance and we're just gonna watch it come up. In order for me to do that, I need to log into this server from the other side because I'm going to kill this other one. I'm going to say SSH to this client. Okay. Now, I'm going to do a for loop to query for github.com, right? So it's querying github.com. I look at the logs here. Tell f var log squid access, right? You can see the requests are coming in, right? Now, do we have any questions, Mr. Owen?
I'm not seeing any.
Okay, so the IP address of this host, it happens to be 159, right? So I'm just gonna keep looking at the logs. I'm gonna terminate that instance. EC2. I can't believe we ran out of time. I got too excited.
It's okay. Yeah. Well, we're not going anywhere, so
150.
always reach out.
I'm going to terminate this instance. I just want to make sure that that's the correct IP address one more time. Can't delay it anymore. 3159. So this is the correct instance. I'm going to terminate this instance now. And I'm going to start the timer. So now notice that, oh man, I logged into a wrong instance. All right. So anyway, let me start the timer now and I'll log back into the instance that is running. Okay. I'm going to log into the EC2 instance that is still up and running and log back into that client. And I'm going to log into a client that was in A. Oops. And I'm going to run that query again. It's not obviously not going to be working because the system is down. Make sure you don't have any questions, Mr. Owens. I would hate not to answer any questions.
No, I'm double checking. I think we're just find a stopping point next couple of minutes.
Okay, great. So right now the query is not working because the system is down, and I have the timer going, folks. Again, I've timed it at 2 minutes and 59 seconds. Let us see how long it takes this time around. It would be great if anybody has any question. We only have 3 minutes left.
So just while we're waiting, right? I mean, I'll ask a question. I mean, what did you feel was the hardest part in this approach?
So, yes, absolutely. The hardest part is, again, always the logic, right? Just trying to think, what would be the best scenario? I have a failure. How would I recover? Some folks opted to update the routing table, right? The system goes down. Maybe you have multiple proxies running at the same time. It gives you double the cost, right? So you would have 2 proxies running. They would be like almost highly available. You know, it detects the failure. It just falls over to the other one. What happens though is if you have 2 availability zones, that means you have 4 proxies. Again, it's double the price. So if you have 5 availability zones, and that's 10 proxies that you're always running, it's going to be on a hot, right? That's one of the things. Again, I also try to update the, use a network load balancer, but I couldn't forward the routing through it. So as you can see, guys, this is coming up now. Let me see if it's running traffic yet. Still not yet. How much time do we have left here? 2 minutes and 49. I give maybe 10 seconds or so before it starts routing traffic again.
Climactic end here.
Yeah, it's still initialized. So as you can see, though, I mean, the server fell, right? The failure was identified, and the system, it's already being rebuilt. It's always going to keep the same count, right? And somehow it's shutting down. I didn't pray to the demo gods. That's it, guys. We ran out of time. Yeah.
All right, so that's good, right? So again, like I said, taking a new approach to an old problem. We're happy to continue the conversation for those of you who found this interesting. And yeah, that's just our Contino way, right? We like to sit with people, share things, transfer the knowledge. Problem shared is a problem solved.
Absolutely. Thank you, folks. Thank you for your time. I guess we'll wait for the next one.
Okay. Thank you.
Thank you.